Hello everyone. Today I'm going to talk about the performance optimization of SVE enabled ARM processor A64FX using Fujitsu compiler. Supercomputer Fugaku achieved rank number 1 at the top 500 HPCG, HPCAI, and Graph 500 at ISC20 in this June. Fugaku achieved 416 petaflops in the top 5 HPL benchmark and also achieved 1.42 exaflops in the HPC AI benchmark. The overview of A64FX, Prime HPC FX 1000 and FX 700, and also brief overview of Fujitsu compiler. Then I'm going to our main topics, performance optimization using Fujitsu compiler 3. Here is a figure of the high-performance ARM CPU A64FX. I use this slide everywhere, so I'm taking some brief overview. The IC is, as you know, ARM v8.2, but AI64 only with SVE scalable vector extension. It's a first enabled SVE processor. The simulated base is 512-bit, and precision support double, single, and half precision. Int 64-bit to 8-bit is also supported. Number of core of A64FX 48 computing core and 4 assistant core. And for the memory, A64FX uses HBM2 memory, so 4 sets of HBM2 provide 1 TB memory bundles. And it only consists of a TOF the 6-dimensional transmission interconnect developed by K computer. And here is figure. You can see the 4 kind of CMG core memory groups and with a HBM2 memory interfacer. And Fujitsu is now selling a Prime HPC FX 1000 and FX 700 for the commercial use. Prime HPC FX 1000 is same as configuration of the Fugaku and supercomputer optimized for large-scale computing. It aims to high performance, high scalability, and high density. And Prime HPC FX 700 is almost same as like a PC cluster for ARM server. It's a supercomputer based on ARM standard technologies using SVSA and SVBR. The product will be on the ARM server ready product in the ARM side. It's easy to use and easy to installation, and also easy to use for the 8-node 2U 19-inch standard rack mount tab. FX 700 uses InfiniBand and air cooling. The difference of the comparison of the FX 1000 and FX 700, the CPU is all same, but the number of cores and the operating frequency different. FX 700 has no assistant core and also operating a lower frequency than that of FX 1000. Node configuration is almost same, but differently interconnect. FX 700 using InfiniBand. The enclosure is FX 1000 dedicated and water cooling, high density, but FX 700 are same as PC cluster 2U rank metal chassis in the 8-node rank chassis and air cooling. Then I'm going to talk about some brief overview of Fujitsu compiler. Fujitsu compiler, system axis like here, the figure. Fujitsu compiler supports Fortran, C, C++, OpenMP. The compiler optimization is in instruction level, also supports loop and loop level optimization. Not only a compiler, Fujitsu compiler system provides core array and MPI for internal communication, and mass library, SSL, BLAS, LLPack and ScalaPack, FFT, and also supports tools for optimization performance profile. In this slide shows some FX features and compiler approaches. From the developing the K computer FX100 and post-K FX A64FX CPU inherits features of their older Fujitsu product and K computer. So, usability including options and programming model are very important to inherit. For the hardware features, compiler target also 512-bit wide vectorization promising optimization and constant folding, such kind of thing. And Fujitsu compiler also support vectorize as vector length algorithms and near advanced schemes. For the hardware optimization, inter-core hardware barrier and sector cache and hardware and software prefetch also supported. The rest of the figure shows some advances from the K computer to the post-K used ARM-based press. CPU instruction different, but almost same microarchitecture is used. And this slide shows the Fujitsu compiler and the language standards support. Fujitsu compiler supports C11, C++14, OpenMP 4.0 fully supported, and C++17, Fortran 2018, and OpenMP 4.5 and 5.0 is partially supported. So let's talk about the optimization of A64FX by using Fujitsu compiler 3. This is the evaluation stream triad on the Prime HPC FX1000. Our stream benchmark is very well-known project, so it's a basic combination of computation and memory access benchmark. And it consists of 4 kinds of benchmark set: copy, scale, art, and triad. And stream triad is most memory intensive one, so we took this triad benchmark. The below this two picture shows some screenshot of each benchmark triad. Left below the figure shows it's very simple OpenMP loops. Sharp plus gamma OMP parallel for and for loop, and M matrices equal B matrices plus scalar multiply and C matrices. That's only. And also below the right side figures, the definition of the each matrices. It's defined as static. So we tried 4 options to utilize some maximum benchmark stream triad performance. It's to utilize the maximum memory boundaries and computation is required. It's 3 kind of important thing. Number 1, boosting memory prefetch access. Number 2, boosting simultaneous operations. Number 3, but removing extra memory access is very important. For example, extra memory prefetch operation, and second is needless memory made access. So we took the 4 kind of set of compiler options. Number 1 is basic optimization option, -03 and -K A64FX, SVE, ARM v8.3 and -K OpenMP. Second option is number 1 plus memory bandwidth option -K assume equal memory boundaries. Number 3 are kind of different. Instead of a memory boundary option, we use a Z-fill and software prefetch option. Number 4 is almost same of the number 3, but without a loop unloading option. I talk about some a little more about Z-fill option. Z-fill option to eliminating needless memory access. Usually, memory write access follow the some before the reads the memory data before writing into the cache line. And Z-fill eliminates extra memory read, which is completely replaced in cache line. And the A64FX Z-fill uses the DCZA instruction to eliminate needless read access. The upper side of the figure shows some when Z-fill is not used. Stream triad requires read B and C matrices and write A matrices. So 3 streams are at least needed. But before writing the A matrices, these are A matrices are needed, so it requires 4 streams. So when Z-fill is used, read matrices are B and C and also write access required. But when that will option instruction that that will option used. Software hardware prefetch disabled and prepare for the zero field cache line onto the L2 cache, and then provided into the L1 cache for using a software prefetch. It not required memory access. So it's only a reduction of one stream. So total 3 streams. It aims to including 25 memory bandwidth upper than that of the when Z is not used. So here's the result. Original stream benchmark. Number 1, one thread performance almost twice as the other thing, but total 48 thread is achieved 629 GB per second. When you use the memory bandwidth option, it's up to the 822 GB per second. Using a Z field and software privilege instead of a memory bandwidth, it achieves up to the 848 GB per second. And without unload option, a little bit higher than that, a little bit. So what's happening in the compiler optimization? Number 1, in the case, so it is analyzed using minus n list equal t, the minus scale of the message equal to option. This is required, so it's a kind of each source LSD suffix option. So you can see the line 343. So use a program OP parallel 4. It's a optimization result. Assuming the optimization is vector length 8 is okay, and using a software pipeline and hardware prefetch for the A, B, and C, and A, and parallelized vectorized. And for the number 2, it recognizes for the memory bandwidth option a little bit different. Software SIMD and software pipeline okay, but the prefetch hardware is C and B, and for the software prefetch for use A, and we also use a Z-free option. Just difference of some difference of optimization. So number 3, option number 3 is a kind of we eliminate the hardware prefetch only for software prefetch and Z-free. That's the difference. So in some cases, it's not optimized for program sample. Because the basic program is statically allocated, but in this case, using a memory line allocated. So A and B and C matrices is given by the pointer. In that case, this variable can be changed. So this comment does not recognize that kind of operation, SIMD and vectorized. In this case, you can change some of the source code by using a constant underscore restrict. For the definition of some another variable C and B and A, and that is okay to something like that, same option. So here is summary of this talk. So I talk about some performance optimization using Fujitsu compiler stream triad. To utilize maximum memory bandwidth and computation and boosting memory prefetch access and boosting similar operation, but also removing extra memory access, extra memory prefetch and operation and needless memory read modify write. So we achieved some over 800 GB per second stream triad band. Here's the end of talk. Thank you for listening.
Hello, everybody, and welcome to the 2020 Research Summit, Day 2. And we've got here today Professor Shinji Sumimoto from Fujitsu, who is a senior architect of the platform software division, and he's actually in charge of the technical development of supercomputer Fugaku. And I'll let him introduce himself further, and then we'll start taking questions. Shinji, would you like to say a few words?
Okay, thank you for listening to my presentation. It's only 15 minutes. It's difficult to show many things, so please could you free to ask me. If I can answer your questions, I can.
Thank you. So we already actually have quite a few questions from the audience. So thank you for everybody asking questions. We'll take it from the top. first one is, could you identify the external interface of the A64FX other than Tofu or PCI Express?
A6 does not have PCIe and TOEFL, but maybe for the extension primary PCIX 700 using connecting some of PCI Express switch, and then go to some many of device can be accessed. So it's easy to expand.
Okay.
But A64 only have the two interface.
Okay, thank you. It's useful to know.
Mm-hmm.
Next question is, how does the ZFIL instruction interact with cache coherence mechanisms?
Yeah, ZFIL instructions are, completely inside the cache. So, so different core, it does also maybe a side effect. So cache coefficient does not keep. So that's a problem. So you need to very carefully to use a ZFIL option.
Okay. Next up is one of our audience is perhaps a bit confused. So they're saying they may have misunderstood something, but are you generating code for fixed 512-bit length, vector length agnostic, or both? And if you do vector length code gen, can I pick the assumed width of my vectors?
Fujitsu compiler produce each one, but fixed length or VL, vector length agonist. That's the option. And also fixed option only can be set for each 128-bit and 258 and 512-bit. So
Okay.
in the fixed list, yes.
Oh, perfect. That's a nice easy one. Also, so there are lots of interesting options to optimize bandwidth. Would it be possible to have those picked automatically for us? Any plans to do some sort of automatic flag selection?
Okay, but the bandwidth of tuning is very, very difficult because it's a single core inside, it's okay. But many core and core location, how many lengths and how many pages. So it's difficult. So currently, we are not some planning some very easy option, but in this case, we provide minus k assume my equal memory bandwidth. That is a very easy way to. And also, there are so many cache line options. For example, minus k prefetch line. This is for L1 cache, and minus k prefetch line minus S. It's also such kind of option. If you select some number, it can be set. But if you are not set, predefined value in the compiler can be filled. So if try so many things and try and error and keep it. So and also you can maybe measure some performance using performance tools. Our performance tool or maybe ARM tool can be used.
Okay.
So it's a combination, the compile, measure, evaluation. That's a tuning phase. It's very important.
I understand. Oh, thank you. There is another question from the audience, so which is, the compiler infrastructure seems to be based on LVM or other than GCC, but they're not sure. Is the compiler written from scratch, or are they based on another compiler infrastructure?
Okay, that's a good question. We have been developing a Fortran C compiler only over 30 years. So in that case,
Okay.
our thread mode is basically completed by my own. However, now we are moving to the LMVM's compiler. So C compiler has two options. And I mean, thread maybe in this place, I use the thread mode. There are no option, but you can also use a C-lang option for C++. Maybe our partial compiler is not so good at some of very, very new C++ standardization. So if you have so many complicated C++ code, you had better to use some C-lang mode. Otherwise, thread mode is faster than. And also, C-lang option now in the under development, so step by step. So sometimes it does not go make us good results. In that case, you use some of test the traditional compiler. So I show the option, some of the some list option. You can see the how Fujitsu compiler produce some of the optimization. You can see the easily. So please use two kind of compiler to your software for each. Thank you.
Okay, thank you. Hope that answers I think that answers very well the question, so thank you. I do have some of my own as well. So in your opinion, what has been the most difficult kind of hardware feature of the A64FX that you had to get the compiler to utilize efficiently?
Maybe compiler, maybe the sector cache is very difficult but very effective option.
Oh,
Which
yes.
Yeah.
Can you tell us a little bit about that?
Yeah, sector cache is some of the use of some part of the cache can be used as a local memory. So if you have some of the reusable data can be on top of some cache, sector cache, so the cache does not flashed in the other access. In that case, some of the matrix material is very effective. However, the number of the sector cache size is limited, and maybe using some directive option is not so, this is a very difficult to tune. Yeah, but
I
if
can
the hit,
understand.
yes, if the hit, it's very good. But sometimes that will go, oh, no difference, something like that. Yeah.
Indeed, especially with, in a way, sometimes the little information a compiler even has available. So
Yes.
I can definitely respect how that's not an easy job.
Yes.
In kind of in a similar type, how is your experience with getting the compiler to actually make make use of SVE in general and use it effectively? Just speaking about SVE in particular.
Oh, it's very difficult. And usually our compiler fits some of the traditional Fortran code. It's very strong. However, maybe a newer version is a kind of somewhat of difficulties optimized. But you can see the some of minus LSD option, and that is very effective. And also, C++ code is not so good at. Many of our users can utilize, but some of the difficult. So in that case, you use a Slang mode is better. So and also maybe we understand. So we have so many options. Not so automatic vehicle. This is also like F1 F1 like high speed machine. So it completely detailed tuning can be utilized, but it's difficult to set and understand what kind of meanings. So it needs to understand some compiler technology and how CPU works. If you can use, you can understand how your application runs and using cache and some of the register and something else, it is a very strong tool. But at the first time, it is at the first time it is difficult. But usually minus k first option is the first reach of the many of the option inside. So can I share some of the slides of?
You go ahead, sure, yes.
Can I have time more?
You do have, yes, we do have more time.
Okay.
And afterwards is another question from the audience we'll cover.
Can you see?
Yes, we can see. Thank you.
So this is not the talk slide, but recommended option that some Fujitsu compiler is minus k option. So if you set the minus k option, there's here is several options can be applied. At first, one is minus 03. This is level of patient 3. So this kind of option is breakdown into the so many kind of optimization. So you can see the Fujitsu compiler manual is a completely detailed inside and written. So
Yeah.
and next is a minus KDR line, downward boundary, and second is a minus K value, apply optimization to change the method of mathematical application, and so many of things can be applied at any time. So if you use Fujitsu compiler at first, minus K first is very good.
Okay.
And also this kind of
more options, yes.
more options, yeah. Manage pre-X maybe offsets promote control optimization and manage sim this option is the vectorized loops which contains if construction, so the predication. In that case, if loop includes some if clause, compiler understand such a if clause and can be vectorized and make faster than. Second voice option is skip parallel, automatically parallelization and skip on OpenAP. This is kind of if we have to set some your OpenAP directives. And second is OpenAP with sims. Yeah, and third group is very important. So it's a minus n list T. Maybe I can show you some of the result. It is very important. So why my why my program can not be faster? It's very easy to understand.
One question actually to that: does the compiler take into account NUMA effects, because clearly the chip is because it's got 4 classes within it?
Yeah, Fugaku does not provide some NUMA directly.
Okay.
Because it can be some, but we can choose some of memory timing, for example, pre-patch option. If you use hard patch does not program, but software pre-patch we can program. So,
okay.
Yeah, so my option,
You've got that. I was going to say, we've got 1 minute left, and we've got one more question in from the audience.
Okay.
So could you identify why the A64FX and the compiler have not used the usual kind of structure of CPU and GPU? In other words, the GPU-like accelerators are not in the A64FX.
Because we don't have some GPU products. So
Okay.
Stage. Yeah.
Okay. Well, thank you very much. This has been wonderful. If I was going to say, I know there are other kind of networking opportunities here during the summit.
Yeah.
So if the audience still has questions for Shinji, please find him around. You can also set up a meeting and talk to him one-to-one if that's something you prefer to do.
Yeah.
And I'd like to thank you again for a wonderful presentation and a very, very engaging Q&A. And I hope everybody's questions were answered well. And thank you for joining us today.